This is a book summary of mathematics, form and function. A comprehensive introduction to the foundations and philosophy of mathematics, examining how formal structures arise from basic notions like numbers, space, and motion, and how various foundational viewpoints relate to mathematical practice. Written by Saunders Maclane. The book is 463 pages long and was released in 1986 by Springer Verlag. The chapter argues that formal mathematics grows out of concrete human activities, counting, labeling, measuring, moving, and is crystallized into formal structures that capture the common patterns of these activities. It introduces mother structures at the heart of the subject: sets, transformations, groups, order, and topology, showing how basic notions such as natural numbers, cardinality, and bijections arise from counting and comparing collections, how infinite and denumerable sets are defined and related, and how permutations and symmetry lead to transformation groups and the abstract notion of a group, with its unit and inverse, along with homomorphisms and isomorphisms. The text then develops linear order and order types, e.g., 1, 2, 3, 4, and the real numbers characterized by completeness, density of the rationals, and the least upper bound property, and moves to space via metric spaces, the triangle inequality, and the idea of distance, which together motivate rigidity of motions and symmetry. Boolean algebra is presented as the algebra of subsets under intersection, union, and complement, with lattice structure via inclusion, while topology emerges from continuity defined via open sets and neighborhoods, culminating in topological spaces and mixed structures like topological groups. Throughout, the author emphasizes abstraction, generalization, axiomatization, and the idea that many mathematical notions admit multiple models, illustrating these themes with concrete examples such as square and polygon symmetries, cyclic groups, and the relations between geometry and algebra. This chapter shows how the natural numbers arise from counting and how their arithmetic follows from a tiny axiomatic core. The P-note postulates, zero, successor, that zero is not a successor, injectivity of the successor, and the induction principle. It explains that all the usual laws of addition and multiplication, commutativity, associativity, distributivity, can be derived from these axioms, and that the induction axiom enables proving broad universal results, including the binomial theorem. It introduces the recursion theorem, which guarantees a unique function f, n right arrow x given an initial value a and a step function g, and shows how addition, multiplication, and exponentiation are defined by primitive recursion, with the Peano system determined up to isomorphism. The text then surveys number theory consequences that follow from this foundation, such as the division algorithm, prime factorization and the Euclidean algorithm, the prime number theorem, and classical results, e.g., sums of squares and cubes and conjectures, Goldbach-Mordell. It then extends n to z by adjoining negatives, and to q by adjoining fractions, preserving the same arithmetic structure and illustrating multiple equivalent constructions. The discussion of congruences modulo m and Euler's phi function, the Chinese remainder theorem, and the algebra of congruence classes follows. Finally, cardinal numbers via equinumerosity, bounded comprehension to avoid Russell's paradox, and ordinal numbers as order types of well-ordered sets are developed, leading to the view that numbers admit many equivalent descriptions and that mathematical structure, preserved under isomorphism, underpins number theory. The chapter traces geometry from its concrete origins in spatial activities, motion, construction, measurement, and fitting shapes, to a precise deductive framework, showing how basic figures, points, lines, triangles, circles, planes, solids, give rise to a coherent system of facts and proofs. It presents Hilbert's plane geometry axioms, incidence, order, congruence, parallelism, and continuity, and the move from intuitive pictures to an austere axiomatic foundation, including Pasha's axiom and the familiar congruence theorems, e.g., SAS, that justify rigidity and congruence. The parallel axiom is discussed not only in its Euclidean form, but also in its independence, prompting the development of non-Euclidean geometries. Hyperbolic geometry, angle sums and triangles are less than 180 degrees, with models showing relative consistency via pseudopoints and pseudolines, and elliptic geometry, no parallels, modeled by great circles on spheres. The chapter also explains geometry as a theory of magnitude, describing how unit length and similar triangles can construct and compare real magnitudes, rationals and irrationals, and how angle measures relate to radians. Geometry by motion then recasts geometric structure in terms of rigid motions, translations, rotations, reflections, forming groups that act on geometric objects, producing concepts such as cosets, isotropy, and orientation. These ideas extend to three-dimensional space, where solid geometry uses analogous rotational groups. Finally, the text reflects on whether geometry is a science, noting its deductive nature, multiple consistent geometries, and its deep connections to logic, continuity, topology, and the broader mathematical framework. This chapter traces how real numbers arise as a universal scale for measuring and comparing magnitudes, distance, weight, time, temperature, etc. Once a unit is fixed, so that a single line with origin and unit can represent all such magnitudes, this scale is complete, containing irrational and transcendental distances and complete enough to support a single continuum of quantities. Magnitudes can be framed arithmetically or geometrically, with angles linked to linear measures via radian arcs and measurements of areas or volumes reducible to the same scale. The real numbers thus provide a common framework for diverse physical magnitudes. Basic operations of addition and multiplication on magnitudes give the familiar real number algebra, organized by the axioms of an ordered field, and the Archimedean law ensures every real is approximable by rationals, and that between any two reals there is a rational. Convergence, limits, Cauchy sequences, and infinite series formalize approximation and continuity, with several equivalent completeness axioms, Dedekind cuts, Cauchy completeness, Weierstrass, tying the ideas together. The text also presents arithmetic constructions of the reals from Q, Dedekind cuts, and Cauchy sequences, situates the reals within vector analytic geometry, vectors, bases, linear transformations, coordinates, inner products, and the trigonometric connection via sin and cos, and then builds complex numbers by adjoining I, with polar form and multiplication as rotation and scaling, illustrating the fundamental theorem of algebra and related concepts like conjugation and stereographic projection to include infinity. Finally, quaternions are introduced as a non-commutative four-dimensional division algebra tied to spatial rotations, underscoring how algebra generalizes geometry and how 19th-century developments expanded the scope of mathematics. Chapter V traces the evolution from informal ideas of dependence to a precise, set theoretic notion of function. A function is a set of ordered pairs with a domain X and a codomain Y, with composition, inverses, and the key notions of injection, surjection, and bijection arising from how elements map and relate. It discusses how functions appear in many guises, from algebraic formulas and graphs to rules, tables, and geometric or physical dependences, and notes that a function's identity depends on its codomain, not just its values. It then extends to maps that are not numerical, such as geometric transformations and linear transformations represented by matrices, and introduces the broader view of functions as structure-preserving maps between spaces. The chapter proceeds to transformation groups, illustrating how symmetry and structure are captured by groups. Examples include SN-NN, GLN, SLN-ON, the Erlanger program linking geometry to its transformation group. It then moves to abstract groups, Cayley's theorem, and constructions such as direct and semidirect products, extensions, normal subgroups, and quotient groups, highlighting inner automorphisms and conjugation. Galois theory is presented as the use of groups to understand polynomial solvability by radicals, via splitting fields and Galois groups, including the correspondence between intermediate fields and subgroups and the solvability of quintics. The chapter closes with developments in constructing and classifying groups, notably Sylow subgroups, free and dihedral groups, and the monumental classification of finite simple groups, including sporadics like the monster, underscoring the deep unifying role of group theory across arithmetic, geometry, and physics, all tied to the notions of image and composition. Chapter VI surveys calculus from its practical origins, Archimedes, area pinching, early tangent constructions, and the move to instantaneous rates, through Newtonian mechanics and Kepler's planetary motion to a rigorous framework built on limits rather than infinitesimals. It explains integration as the limit of sums, Riemann, and derivatives as instantaneous change, united by the fundamental theorem that ties differentiation to integration. The text highlights applications in mechanics, Newton's laws, projectile motion, planetary orbits, and then the general use of differential equations, including existence and uniqueness, Picard, under Lipskitz's conditions and the idea of phase space. Foundations cover continuity, uniform continuity, and the Hein-Borel compactness essential to convergence. Approximations lead to Taylor's theorem and power series, while multivariable calculus introduces partial derivatives, the chain rule, gradients and cotangent tangent spaces, and differential forms, culminating in line and surface integrals and the Gauss-Green, Stokes theorems. Finally, calculus becomes analysis. Lebesgue integration, L2 spaces, Fourier series, and PDEs, wave, Laplace-Dirichlet problems with harmonic functions, illustrating the deep interconnections among algebra, geometry, topology, and physics. Chapter VII develops linear algebra as the study of linearity over a field, starting from vector spaces, subspaces, bases, and dimension, then connecting linear maps to matrices via coordinates and emphasizing composition and the rank-nullity relationship. It introduces eigenvalues, eigenvectors, and similarity to diagonalize endomorphisms, notes the Cayley-Hamilton theorem, and extends to dual spaces and bilinear pairings, leading to the adjoint and inner product spaces. Orthogonal and unitary transformations are treated, with the principal axis and spectral theorems, and the structure of self-adjoint and unitary operators. The text then develops bilinearity and tensor products, showing a universal encoding of bilinear maps and the functorial behavior of tensors. Exterior algebra and differential forms arise from appropriate quotients of tensor algebras, including determinants as exterior products. Quotients give quotient spaces and modules. The section culminates with rational canonical form via invariant factors, the role of modules over principal ideal domains, e.g., Z and Fx, and corollaries for finitely generated abelian groups, tying similarity to canonical forms to module theory and touching on Galois theory. Throughout, geometry, analysis, and algebra are unified by the language of vector spaces, dualities, and linear transformations. Chapter VIII, Forms of Space, surveys how perceptions of space give rise to a spectrum of formal structures, from arc length and curvature to topological spaces, manifolds, and sheaves, emphasizing the shift from intuitive pictures to intrinsic geometric descriptions. It treats curvature in depth, plane curves via osculating circles and arc length as an intrinsic parameter, space curves with the Frenet frame, and surfaces where Gaussian curvature can be described by principal curvatures and the shape map, or intrinsically, from the first fundamental form ds2. Gauss's theorem shows Gaussian curvature is determined by this intrinsic metric, connecting curvature to angle sums in geodesic triangles and supporting the notion of curved space. Arc length, the first and second fundamental forms, and metric concepts generalize to intrinsic geometry, with the idea that curvature and distances can be defined without reference to an ambient space. The text then explains many-valued functions and Riemann surfaces, illustrating how multi-valued functions, e.g., W2 equals Z or W2 equals Z2 minus 1, Z2 minus 4, become single-valued on appropriately constructed surfaces via branching and gluing. It continues with manifolds and classic examples, sphere, torus, Möbius band, projective plane, discussing orientability and genus and the Atlas overlap approach to manifolds. Smooth manifolds bring charts with smooth overlaps, tangent and cotangent spaces, differential forms, vector fields, jets, and the structure sheaf. Finally, Riemann metrics assigns smoothly varying inner products to tangent spaces, enabling path lengths and areas, while the notion of sheaves provides a unifying language for spaces of functions. The chapter concludes that geometry is not a single space, but an intrinsic, multifaceted study of space across many formulations. The chapter surveys the deep and ongoing interaction between physics and mathematics, showing how the same ideas recur in both fields from Newtonian mechanics to modern geometric formalisms, and illustrating this through classical and contemporary examples. It begins with Kepler's laws and Newton's derivation of planetary motion from F equals m and the inverse square law, introducing angular momentum, the area law, and the fact that orbits are conic sections, ellipses for planets, and that Kepler's laws follow from Newtonian mechanics. It then develops core mechanical concepts: momentum, work, and energy, including the conservation laws and the relation work equals the change in kinetic energy, with the harmonic oscillator and phase plane as key illustrations. The text introduces Lagrange's equations in general coordinates, the idea of generalized forces, holonomic and non-holonomic constraints, and the pullback of the work form, emphasizing that the equations hold invariantly under coordinate changes and connect to tangent bundles. Then presents Hamilton's formulation via the Legendre transform to the Hamiltonian, Hamilton's equations in phase space, and Hamilton's principle of stationary action, followed by the Hamilton, Jacobi theory, and the principal function S, which links mechanics to optics, Fermat's principle, and to quantum mechanics in the h-right arrow zero limit. The spinning top example, Euler angles, moments of inertia, elliptic integrals, and precession, illustrates dynamics on rotation groups. The chapter concludes with reflections on the form of mechanics, its tricks versus ideas, the role of differential forms and symplectic geometry, tangent and cotangent bundles, canonical transformations, Lie groups, and the broader mathematical structure underlying physical theories. Starting from the simple device of a joining I with I2 equals -1, the The chapter develops how complex numbers model the plane and how complex differentiability gives holomorphic functions whose theory is remarkably strong. The Cauchy-Riemann equations link the real and imaginary parts, force analyticity, imply conformality angle preservation, and connect to harmonic functions, the real parts, with physical interpretations in electrostatics and potential flow. It then extends real functions to the complex plane via the exponential, sine, cosine, and logarithm, noting the logarithm is multivalued and is made single-valued on Riemann surfaces. Examples include the exponential mapping strips to the plane, the polar form z equals rho theta, and the universal coverings EW, and its inverse log z complex integration follows, establishing the Cauchy theorem and Cauchy integral formula, which yield open mapping, maximum principle, and the capacity to differentiate and integrate series term by term. Power series define radius of convergence. Liouville's theorem explains why entire bounded holomorphic functions are constant, and Laurent series classify singularities, removable, poles, essential, with residues underpinning the residue theorem. Analytic continuation and monodromy lead to Riemann surfaces as the natural setting for multivalued functions, via coverings and the fundamental group, e.g., Z for the punctured plane, free groups for unions of circles. And the germ-sheaf viewpoint formalizes holomorphicity as local data glued by cross-sections of a local homeomorphism. Together, these threads, analysis, geometry, and topology, elucidate conformal maps, analytic continuation, Riemann surfaces, and the unifying role of germs and sheaves in complex analysis. Chapter XI argues that mathematics rests on a concise foundation built from sets, logic, and formal inference, typically via the Zermelo, Frinkel set theory, ZF, with replacement, and the axiom of choice, together with a first-order predicate calculus. It explains how almost all mathematical objects can be coded as sets and proofs reduced to finite inferences, and it covers foundational developments such as Gödel's incompleteness theorems and independence results, most famously the continuum hypothesis, shown independent of ZFC by Cohen's forcing and by Gödel's constructible universe, demonstrating that there are multiple viable set-theoretic universes. The text also develops the language of first-order logic, including propositional and predicate calculi, bounded comprehension, and formal proof, with Peano arithmetic as a key example and remarks on completeness and compactness. In parallel, it presents category theory as an alternative or complementary foundation, focusing on categories, arrows, functors, natural transformations, and universal constructions, products, pullbacks, coproducts, exponentials, and the role of adjoint functors. It introduces the notion of a topos, subobject classifiers, and intuitionistic logic, with concrete instances, set, GRP, top, vect, and time-varying examples such as presheaves and sheaves. The chapter closes by comparing foundations and organization, arguing there is no single basis for all of mathematics, but that both set-theoretic and categorical perspectives offer essential, interrelated tools for organizing and understanding mathematical structure. The chapter The Mathematical Network presents mathematics as a tightly connected network of formal rules, concepts, and axiom systems, grounded in human activities and scientific questions, and continuously developed by conjecture, problems, abstractions, and the drive to understand more. It emphasizes the formal character of mathematics. Calculations, proofs, definitions, and axioms operate independently of meaning or application, with examples ranging from arithmetic and Peano's axioms to Hilbert's geometry and the predicate calculus, and with the idea that even topics like holomorphic functions or set theory are best understood through formal definitions and the manipulation of symbols. Then foregrounds the role of ideas, ubiquitous guiding notions such as manifolds, continuity, curvature, and eigenvalues, that can have multiple formal realizations, and shows how mathematics is a network whose nodes subjects are richly interlinked with each other and with human activities and sciences, physics, economics, engineering, including deep connections like the parallel between algebraic number theory, Riemann surfaces, and algebraic geometry via ideals, valuations. In function fields, the text also discusses the rise of specialized subjects, the central role of problems, e.g., Fermat's last theorem, Burnside's conjecture, the Poincaré conjecture in driving progress, and methods for understanding analogy, examples, proof analysis, invariant formulations, shifts of attention, along with generalization and abstraction, generalization, analogy, abstraction by deletion, shift of attention. It notes novel ideas arising from science, delta distributions, solitary waves, fast matrix algorithms, the limits of fuzzy sets, and tackles the question of truth by arguing mathematics is true insofar as its formal systems are correct and productive, not as a claim about physical reality, thereby rejecting ontological Platonism while embracing a mythological view of mathematical ideas as aids to understanding. The chapter closes with preferred directions for research, outlining how extraction of ideas, formalization, establishing connections, and understanding proofs and concepts guide future work, and it surveys how mathematics evolves through origin, organization, dynamics, foundations, and the ever-present tension between formal structure and practical applicability.